Okay. Am I audible clearly now? And is my screen visible to you?
Yes, sir.
Okay, great. Okay. So let us start with the first method, that is direct method. Let me change the thickness. Direct method. And remember, I have told you that if I consider a spring with constant k, and let us say if I give the displacement x, apply, let us say I have applied force F and it displaces by x. Okay. Now in that case, I can write F is equal to kx, right? Minus kx actually, because the internal force, if I say, that would be minus kx, and this external force will be plus kx. Okay. Now, in a similar way, if I take this simple rod and if I apply this force P, let us say L is the length of this rod, A is the area, and E is the Young's modulus. Now, if it has the elongation of x, then I can write x is equal to L by A, and I can write P is equal to A upon L into x, right? So this term I can call it as x, k is equal to P is equal to k into x. So A upon L is similar to, A upon L is similar to k or analogous to k in spring. Okay. Now, let us take a spring. Okay. Let us consider this as node 1 and this as node 2. Okay. And I'm applying let us say ui as the displacement at this displacement vector at this node 1 and uj displacement at this, and let fi be the force at this node and fj be the force at this node. Okay, for this spring. Now I can write fi is equal to k into ui minus uj. Okay, I can write this fi is equal to ui minus uj, whatever the difference with the displacement, multiplied by k. Similarly, so let me expand this. k into ui minus k into uj. Okay, that is my fi. Similarly, at this node 2, I can write, let me call this as I and j node instead of 1 and 2. So at j node, I can write this fj force is equal to k into uj minus ui, right? Uj minus ui. Okay. Now rearranging this, I can write k into uj minus k into ui. Let me take this as a first term, k minus k into ui plus this k into uj. Okay, that is my fj. Now I have equation 1 and equation 2. Now if I say let me consider this equation as something like this 3 3 is equal to 3 is equal to 4 into x minus 4, this is same constant, 4 into y. And let me consider this equation something like 9 is equal to minus 4 into x plus 4 into y. And if you remember, in 10th class, you used to write this, or like in the matrix form, like 3, 4 is equal to here 4, this 4, now this minus 4, now this minus 4 here, this 4 here, into x into y, right? This way, I can write these two equations like fi into fj is equal to k minus k minus k, k is into ui huge. Okay. Now let me take k as common from this matrix. So k into 1, here it will be 1 minus 1 minus 1 1 into, this will be same ui into ui and uj. Okay. Now I can put this k as, for simple 1D rod element, I can put this k as a upon l, right? A simple rod, I can put that as 1 minus 1 minus 1 and 1 into ui and u. So this is my k matrix. This is my K matrix. Understood? What we have done? We have written the force at this node I, then force at node J, and we have written that in the matrix form. And then we have just put the value of K. That's it. Now, this is simple. That was the direct method. Now, if we go for variation method, I can write strain energy as U is equal to integration of over the volume 1 upon 2 epsilon transpose into sigma d. Now, this might look like somewhat difficult to you, but let me take you to the equation like 1 upon 2 sigma into E. This equation may be familiar to you. So that is strain energy and if I multiply here with volume V and instead of this V, if I take volume here, strain energy per unit volume, that is the expression for strain energy per unit volume, right? Sigma into E into 1/2. Now this is same expression here. Here we have dV and we are integrating that. Now here this is strain and this is sigma. Now we have epsilon is equal to B into D, right? Strain displacement matrix into displacement matrix for element. Now, if I want to write epsilon transpose, then I will have simply D transpose. It will come here and transpose, and we will go here and transpose. Multiplication of them. Okay. Epsilon transpose. Now, putting these values here and putting now we know E is equal to sigma for epsilon. Now I can write sigma is equal to A into epsilon, right? So putting this and this in this equation, I will get U is equal to Now, for this rod with cross section A, I can write dV as equal to A into dx, right? Because area is constant, and I can write this way because area is constant. So I can rewrite this integration as 0 to L 1 upon 2. Instead of epsilon transpose, I will write this d transpose into b transpose into sigma has to be written into A into epsilon into A into dx. Now, taking all this outside, 1 upon 2 into 1 upon 2 into d transpose into d integration of 0 to L. What is there? B transpose E into A into B dx. Okay. Now I have now this term. Okay. If I want to write, let us say, okay, first I will explain regarding the spring. Okay. If I want to write strain energies for spring, I will write as 1 upon 2 k into x square, right? 1 upon 2 k into x square. That is my strain energy for spring. Now, x here it is displacement. Now, d into d, I can d multiplied by d transpose is similar to the x square, right? This is similar to the x square. I have 1/2. Now, this remaining term must be k. It should be k. Now, I have k is equal to, and equating this like equating this analogy, I have 0 to L this B transpose E A B dx. Now this B matrix, that is strain displacement matrix, is for 1D element. I have the B matrix as is equal to 1 upon L 1 minus 1. So B transpose can be written as 1 upon L 1 minus 1 sorry, that is, this is -1. As we start from this, if this is 0, this is -1, this is plus, so 1. So it is -1 plus 1, and this is -1 plus 1. Okay. Now this is B transpose. Putting this B and B transpose in this equation, I will have K is equal to integration 0 to L 1 upon L -1 1 into A into 1 upon L -1 plus 1 into dx. Okay. Now taking this EA and L into L constant outside and multiplying this -1 1 into -1 1. Multiplication of this matrix will be -1 into -1 1, -1 into -1 into -1 1, 1 into -1 -1, -1 into 1 -1, 1 into minus, so 1 into 1 1 into 1 1. So taking this outside, EA, I don't know what happened to this pen, EA upon L square into, I have this 1 -1 -1 and 1 outside. Now if I integrate this 0 to L, and here I have dx, so I don't have anything, 1 into dx, so this is like x. Integration of dx will be x, and if I put the limit 0 to L, I will have L minus 0, that is equal to L, right? So E into A upon L square into this matrix 1 -1 -1 1 into this L. Okay, now L gets cancelled. So I have EA upon L into this matrix. Now this is your K matrix. Now just observe, is this matrix same? Is this matrix same as that of this matrix? Just this alteration, like here and here, but it is like cumulative, so no worries. E by L into 1 -1 -1 1, right? So by both the method we get same matrix. Is it clear to you? Any doubt in this? Aniket, Kunal, Ramesh. Any doubt? Aniket, Kunal, are you there?
Yes, sir. No doubts.
Okay. So now we have seen both the methods, direct approach and variational approach. Now that was for just simple 1D element. Now if I have number of elements, but before going for number of elements, let me talk about relay reads technique. Reads technique. Now, if I consider this body, I have infinite number of points in this body, right? I have infinite number of points in this body. But, and this infinite number of points, at each point, I will have different degrees of freedom. Like this point can move in, let us say y, x, or z. All these points will have different degrees of freedom, and there are infinite points in this body, so it will have infinite number of degrees of freedom, right? So this solid consists of infinite number of degrees. Now if I want to solve this number of, and so at each point I will have to write differential equation, and solving these differential equations by applying the boundary condition for infinite number of degrees of freedom is not possible. Now, what we do, instead of these differential equations with the relay race technique, we consist functionals. Instead of these differential equations, we consider functionals. Okay. And we assume some functional. Now, let us consider displacement field such as u is equal to, and that can be assumed to be, that can be assumed as b into I into alpha I. Alpha is function of x, y, z. Okay. I varies from 1 to p. Similarly, for phi also, I can write b j into alpha j x, y, z. J varies from p plus 1 to q UVW UVW is equal to summation of b into k into alpha k x y z. K varies from q plus 1 Ah. Now I am assuming my displacements as displacement as some functions. Okay, this alpha I, alpha j, alpha k are some polynomials. Okay, now if I write my potential energy, phi will be the function of this b1, b2, b3 until b. And to have this potential energy minimum, I can differentiate with respect to this different variables. I can equate have the minimum potential energy. Now I can write these equations for n number of n number of equations, and I can put my boundary condition and I can solve them. That will give me this unknowns EV and W. Okay, I can write this n number of equations, and by writing different boundary conditions, I will get unknowns. So this is Rayleigh's technique to solve this engineering problem. Now, let us say I have two springs. Earlier it was only one spring. Now I have two springs. Node 1, node 2, node 3. Now I want to write, let us say this has K1 stiffness and this has K2 stiffness. Okay. Now this I can call element 1 and this I can call element 2. Okay. Now for element 1, I can write stiffness matrix as K1 minus K1 minus K1 and K1 plus K1. Okay. For element 1, I have nodes 1, 2, 1 and 2. For element 2, I can write K2 minus K2 minus K2 plus K2. Node 2, 3, 2 and 3. Now, for the total combination, if I want to write my stiffness matrix, then what I need to do, I will write 1, 2 and 3. 1, 2 and 3. Okay. Now at 1, 1, 1, 1, I have K1. Okay, I will write K1. Now at 2 and 1, 2 and 1, I have minus K1. I will write minus K1. Now at 1 and 2, at 1 and 2, I have minus K1. 1 and 2, 1 and 2. So here I will have minus K1. At 2 and 2, I have K1. So I will write K1 here. This matrix I have written. Now here, at 2, 2, I have K2. So at 2, 2, I will again write K2 here. So plus K2, K2. Now at 3, 2, I have minus k2. At 3, 2, I have minus k2. I will write here minus k2. At 2 and 3, column 2, row 3, I have minus k2. Column 2, row 3, minus k2. I will write minus k2 here. Now column 3 and row 3, I have k2. So I will write k2. All values, whatever there, I have written. And whatever empty, I will replace that with 0. Okay. So these are my element stiffness matrix KE1 and K element stiffness matrix 2. And this is my global stiffness matrix KG. Okay. So what I have just simply written nodes here over 1 2 1 2 2 3 2 3. Here I have 3 nodes, so 1 2 3 1 2 3, and first I will write value of 1 1, then 2 2 1 3 1, then value of 1 2 2 1 2 2 3 2, then 1 3 2 3 3 3 in this way. So thank you. That's for this lecture, and uh, if you have any doubt, you can ask me. Do you have any doubt? Kunal, Aniket? So we can stop here.